Hey all, welcome back to Cracking the Fang Interviews. Today we are going to talk about question which is essentially considered the fundamental of recursion and dynamic programming. And the question is Fibonacci number, finding the nth Fibonacci number. And this is a interview question which has been asked at Facebook, Salesforce, Amazon, Microsoft. It's pretty much a base question to sort of test your fundamentals of recursive and dynamic programming approaches and how do you optimize them. So let's dive deep. I'm going to start with explaining the problem further. Again, it's on Leetcode. The link to the problem is in the description below. The Fibonacci numbers f of n from a sequence is typically is denoted by the sum of two preceding ones. And it starts from 0 and 1. So the first Fibonacci, the 0th Fibonacci number, I want to be technically correct on the notation, is 0, and the first Fibonacci number is 1. So the nth Fibonacci number is f of n minus 1 plus f of n minus 2 for any n less than 1. Let's look at an example to understand this further. So if you're given an n equal to 2, so the 0th Fibonacci number is going to be 0, the first Fibonacci number is going to be 1, the second Fibonacci number is going to be, it's going to be 1 and 1, 0th first and second. And the second Fibonacci number is going to be sum of the previous two, which is the first and 0th, 1 and 0, and you get 1. So this is the central idea of the question. So how would you think about solving it? The way I'd like to think about this problem is to solve for n, you need to solve for n minus 1 and you need to solve for n minus 2. This tells me you need sub-problems which you can later combine. This is sub-problems later combine to find your answer. And so whenever you come up with this sort of a expression which has some relation with sub-problems, the first thing I want you to think about is recursion and dynamic programming. When I say recursion, I'm going to oversimplify the definition to help you understand the concept. Recursion could mean if I ask you for something, you go and solve for one space, and also you essentially solve for subspaces of the problem or sub-problems. And dynamic programming is essentially you can think of it as a recursion method where you essentially store the solution. So you solve a sub-problem, store the answer somewhere, use it later, and likewise. Let's now focus on the problem and try to break it down and see how recursion and dynamic programming can help us solve this problem. So if I ask you for n equal 5, the fifth Fibonacci number, the way you could solve that is you can further break it down into solving for n minus 1 and n minus 2, so 4 and 3. And the way you could solve 4 is solving for 3 and 2. The way you could solve 3 is solving for 2 and 1. And the way you could solve 2 is 1 and 0. And again, this is a repeat, as you can see. And so on. Now, there's one pattern that we can later optimize, but I want to just briefly mention it so that we don't miss it, given we are already looking at the recursion tree. If you see, whenever you solve for sub-problems and see a duplication of sub-problems, as an example, solving for 3, there is a duplication. You're exactly solving the same subproblem. Solving for 2 is a duplication 3 times. This tells me you can later optimize your program, so you don't resolve or do this duplicated work again and again. So keeping that in mind, the first thing I'm going to do is just implement a simple recursive approach for this problem and take it from there. So for the recursive approach, we're going to solve it right here. I'm going to start writing my Python function. It's going to be def recursive Fibonacci of n. And the base case of the recursion is going to be if n less than equal to 1, you return n. So the reason I do that is the 0th Fibonacci number is 0, the first Fibonacci number is first. You need these to be able to solve for the second Fibonacci number and so on. So this is the base case. Now I'm going to figure out how do I call the recursion or subproblems. The way I'm going to do that is you simply return recursive fibo. Again, this is the name of the function of n minus 1 plus recursive fibo of n minus 2. As simple as that. This is your recursive approach. Now the next natural question is what is the runtime? So time complexity. So as we saw, if I ask you to solve for a case where n equals 5, the fifth Fibonacci number, you're gonna solve for Fibo of 4 and Fibo of 3. Then for 4, the subproblem for 4, you'll solve for 3, 2, for 3 you'll solve for 2, and 1. For 2 you're going to solve for 1 and 0, and so on. So the way you typically, once you have this call stack drawn, the way you typically find the runtime or time complexity is how many actions are you able to take at each level of the call stack. So at each level you take 2 actions, right? These can also be called branches. So branches equals 2. And what is the depth of maximum depth of the recursive tree? In this case, just by doing a simple analysis, you start with 5, you go to 4, 3, 2, and you'll go all the way to 1. So the maximum depth is essentially going to be nothing but n. So the runtime is going to be of the format of branches power depth, and it's essentially exponential. This is a general thumb rule I follow to derive runtime for any recursive program. And in this case, this boils down to O of 2 power n. It's an exponential time complexity. And for space complexity, the maximum depth is how many call stacks you create while running the program, and it's clearly the maximum depth is O of n. Now, the natural question, I ask in all my videos is, can you do better than this exponential program? I think the space complexity is still okay. It can, it want to do better, but the major bottleneck of the program is the exponential time complexity. And as we saw in our previous slide, we had duplication of these subproblems. And Fibo of 2 is never going to change. If we solve it once, we can simply reuse the result across the board. So let's use that to optimize the code further. What I'm going to do is start storing my results. So every time I calculate a Fibo, I'll be storing it in my table. What I mean by that is if I'm being asked to find Fibo of 5, I'll be solving it as Fib of 4 and 3. Once I solve Fib of 3, I can essentially use the solution right here rather than going further and solving it. So the way we can do that is with dynamic programming. Dynamic programming essentially means you're storing results to your subproblems. And the first thing we do is our base cases. Again, this is Python code. And you essentially store the 0th Fibonacci number and the first Fibonacci number. And you start iterating from 2 and so on. So for every number, you append the solutions from the past 2 Fibonacci number. And that way you're able to convert a exponential algorithm into a linear algorithm, since you're essentially going to be going asymptotically going to iterate of O of n to O of n. So dynamic programming essentially allows us to store results to our subproblems and avoid duplication. And that's it for today. Thank you for watching another video of cracking the FANG interviews.